Hey everyone, welcome back to this three-phase series. In previous video, I had given the introduction about that how the three-phase generation takes place and how can we connect the load to the three-phase system. So in that case, we had seen that we had two possible connections, star connection and delta connection. We have also established that the line voltage and phase voltage they are not same in case of star connection, while the line current and phase current they have same value. Also, in case of delta, the phase voltage and line voltage they are same, while the line current and delta current they are not same. So in this video, I'm going to drive the relationship between the voltage current or as well as power in case of three phase system, both star as well as delta. So let's start with the star connection. So if we have three phase supply, which is connected in star, R, Y, B, and this one is the neutral. The voltage of phase R can be written as VR, for phase Y, VY, and for phase B as VB. Now VR can be written as VRN as well, since it's the potential difference between line R and the neutral. This one is actually equal to phase voltage angle 0. Since this is a balanced system, so all the phase voltages they will have same magnitude, so we can write it as VP angle 0. Phase V voltage, also written as VBN, is equal to VP angle minus 120. Sorry, not B, it's Y. Phase Y voltage can be written as VYN, VP angle minus 120, and phase B lags behind phase R by 240. So VB is equals to VBN, VP angle minus 240. So any notation can be used. All these voltages they are equal in magnitude, but they are displaced from each other by 120 degree, since this is how the coils are placed. Now the line voltage is between any two lines. Let's say between these two lines, the voltage is VRY. So when we are writing VRY, it means R is at higher potential than Y. Y between VB and VY is VYB, and between R and B, VBR. So we have to move like in the sequence. We are going from R to Y, Y to B, and from B to R. So voltage VR by VYB and VBR. Now for that, for finding out the three line voltages VRY, VYB or VBR. These are the three different line voltages. What can we do? We can apply KVL. So like for finding VRY, we have to apply KVL over here. So when we apply KVL over here, we follow this path, this one. Since this is the R dash terminal and this is R, so this terminal is considered as negative and this one as positive, negative, positive, negative, positive. VR by means R is positive, Y is negative. Let's apply KVL. If I will start from VR, then it's minus VR plus VRY. All these are phasor quantities. Minus, sorry, plus Vy equal to 0, or VRY, that is equal to VR minus Vy. So also we have written the value of VR as well as Vy. VR is VP angle 0, Vy is VP angle minus 120. So we can write it as VP cos 0 plus J sin 0 minus VP cos minus 120 plus J sin minus 120. So Vp cos 0 is 1, sin 0 is 0, minus Vp cos of minus 120 minus zero point 0.5, sin of minus 120 is minus 0.866. So Vp is common, 1.5 plus 0.866. Now when we change this one to polar form, we find out the magnitude angle. This one comes out to be root 3 times Vp and angle 30 degree. Similarly, we can apply KVL to find out V by V. So when we apply KVL, V by V, it comes out to Vy minus Vb. Vyb is Vy minus Vb. Vy is Vp angle minus 120. Vb is Vp angle minus 240. So when you solve this, you will get the value of Vyb as root 3 times Vp, and angle over here will be 90 degree. Sorry, minus 90. Similarly, you can find out VBR. For VBR, the relationship will, you have to apply KVL. You can consider that here the voltage is VBR and apply KVL over here. So VR minus VB plus minus VBR equal to 0, which gives us the value of VBR as VB minus VR. Again, we have to substitute the value of VB and VR. VB is VP angle minus 240, and VR is VP angle 0. Now when we solve this, we will get the value of this VBR as root 3 times VP angle plus 150 or minus 210, or it can be written as root 3 times VP angle minus 210. Now all these angles which are coming with the line voltages 30, 90, and then 2 minus 210, these are with respect to our reference. Now what is reference? Reference is the voltage of phasor, since this one is VP angle 0. Now let's draw the phasor diagram corresponding to the phase supply. So we will start with the reference. VR, VY, and VB. Our first line voltage, which was VRY, so we can write this one is phasor sum of VR and minus of VY. It's phasor sum of these two. So we have the value of VR. We can draw minus of Vy, and when we have to draw minus of Vy, it means we have to draw it at 180 degree from its original position. So this one is minus of Vy. Now the phasor sum of these two is Vr by, and this angle is 30 degree. This angle is 30 degree. Then we have our second voltage, that is V by V. It can be written as Vy plus minus of Vb, phasor sum of these two. So let's draw the minus of Vb. Minus of Vb, again it means we need to extend this Vb by 180 degree. The phasor sum of these two gives us the value of, this one is minus Vb, this gives voltage Yp, and this angle is 90 degree. And the last voltage is VBR, which is phasor sum of VB and minus of VR. So we have to draw the minus VR first. Minus VR means add 180 degree to VR. This one is minus VR. The phasor sum of minus VR and VB is VBR. Now the this angle, this one is 210 degrees. And if you look from this side, this one is 150. So you can either write it as 1 plus 150 or minus 210. Now what we see over here, this angle is 30. This angle, it will be 30. Now how it is 30? We know that we have already the value of this angle as 120. Then again 120. This one is 120. All these three voltages, they are displaced from each other by 120 degree. So these are at 120. Now if I draw V by at 180 degree, sorry, minus of VB from VB, so it means this total angle is 120. One, this one is 180. 180 minus 120, what we are left with? The angle between Vy and minus of Vb is 60 degree. Since they are equal in magnitude, so their resultant will divide them in equal angles. So that's how we get it as 30 degree, and similarly this one is also 30 degree. So what we have seen that all the line voltages, VR by is leading VR by 30 degree, VYB is leading by VY by 30 degree, and VBR is leading VB by 30 degree. So what we conclude that all line voltages leads the respective phase voltage by 30 degree. Also, what we have seen, whether it's a voltage VR by its magnitude is root 3 times Vp, Vb root 3 times Vp, Vbr root 3 times Vp. So the line voltages, they are equal in magnitude, that is root 3 times Vp. Or in phasor form, we can write VL is equals to root 3 times Vp angle 30 degree. It's better to write it like Vp angle 30 degrees, where Vp is the magnitude of phase voltage and angle 30 is added. So if Vp is at angle 0, so VL will be equal to root 3 times Vp angle 30. If Vp is at angle 10, then VL will be equal to root 3 times whatever the magnitude of Vp and angle will be 40. Like this. So all the line voltage, they will lead the respective phase voltage by 30 degree. It means they are also displaced from each other by 120 degree. Now let's move on to the delta connected system. Since we know that in case of delta connected system, the line current and phase current, they are not same. No, let's draw the delta connected system first. R, Y, B. VR, VY, VB. This is actually R terminals. This is R dash because finishing end of first is connected with the starting end of second. So this is Vy. Uh, this is a positive terminal of Y, negative terminal of Y. So we can draw it like this. So as per the polarities, the phase currents, they will be flowing like this. They will be flowing like this from the positive terminal of the source. This is line current IR, IY, IB. Let's denote this current as I1, the first phase current, I2 or I3. Or you can have some different notation as well. There is no issue. Now what we see over here, that this is a junction. So when it's a junction, it means there is current division. So we have to apply KCL at this junction, over here and over here. But before moving on that, let's write the value of three different phase currents. I1 is IP angle 0. Since our phase R is reference, I2 IP angle minus 120. RYB is the phase sequence which we are considering, RYB. So obviously the current which is flowing in phase Y, that will lag behind phase R current by 120 degree, and similarly the current which is flowing in phase B, that will be lagging behind the current flowing in phase A by 240 degree. So it's minus 240. Now let's apply KCL over here at junction R. So IR is outgoing current, I3 is outgoing current, and I1 is incoming. So we have just one incoming current and two currents are outgoing. We need to find out the value of IR. So it will be equal to I1 minus I3. Similarly, we can apply KCL at junction Y. From there, we will get the value of Iy as I2 minus I1. Because when we apply KCL, Iy is outgoing current, I1 is outgoing current, and I2 is incoming. So I2 is equals to Iy plus I1. So that gives us the value of Iy as I2 minus I1. And the line current is IB. For that we need to apply KCL at junction B. So which will give us the value of IB as I3 minus I2. Now how it is I3 minus I2? I3 is incoming. So I3 will be equal to I2 plus IB. Then IB is equals to I3 minus IB. Now to find out the relationship between the line current and phase current, we have to proceed in the same way as we proceeded for the calculation of line and phase voltage relationship in case of star connection. I'm starting with this IR. For IR, we have to use I1 and I3 values. So IR is equals to I1 is IP angle 0, I3 is IP angle minus 240. So IP cos 0 plus J sin 0 minus IP cos minus 240 plus J sin minus 240. Cos 0 is 1, sin 0 is 0. Cos minus 240 is minus zero point 0.5. Sin of minus 240 is plus 0.866. So it's IP. Real parts are added together. Minus minus plus, so 1.5. Then minus J 0.866. Now when we change this into polar form, the magnitude is root 3 and the angle is minus 30. Similarly, when we calculate not I2, Iy, which is equal to I2 minus I1. So we have to substitute the value of I2. I2 is IP angle minus 120 and I1 is IP angle 0. The solution of this will give us the value of Iy as root 3 times IP and angle will be minus 150. And then the third current IB, which is equal to I3 minus I2. I3 is IP angle minus 240. I2 is IP angle minus 120. So you have to write it as IP angle cos of minus 240 and cos of plus j sine of minus 240, and that solution gives you the value of root 3 times ip, and angle will be plus 90. Now please check these angles as well as the magnitudes by doing the complete calculations. So what we have seen over here, that all the line currents, their magnitudes are root 3 times ip. So we establish one relationship, that IL is equals to root 3 times IP in case of delta connection. Now let's draw the phasor diagram. So since it's about the current, phase R current I1, I2 is second phase, that is phase Y current. They are at 120 degree from each other. And then we have current I3, which is at 120 degree from I2 as well as from I1. So all these angles, this one 120, 120, and this one is also 120. We had already written that IR is I1 minus I3. It means I1 plus minus of I3. So let's draw minus of I3 at 180 degree to I3. So this is minus I3. The phasor sum of I1 and minus I3 is our first line current IR, and this angle is 30 degree. We had already calculated it mathematically. We can see it from the phasor diagram as well. I1 and I3, they are equal in magnitude. This total angle is 60 degree. So they will divide. Their resultant will be at 30 degree, half of the phase difference between these two. Second is, second current is IY, which is I2 minus I1, which we can write as plus minus of I1. So let's draw minus of I1. This one is minus of I1. Phasor sum of I2 and minus of I1 gives us the value of IY. Now this angle is 150 degree. This is what we had achieved by mathematical formulation, and you can verify it over here. From I1 to I2 angle is 120. Between I2 and minus I1, 60. Since they are equal in magnitude, the resultant will divide them in at equal angles. So this angle is actually 30 degree. And from the reference, this IY is 150 degree, and from I2 it's at 30 degree. And the last current, last line current is IB, which is equal to I3 minus I2. So we can write it as plus or minus I2. So we need to draw minus of I2, minus I2. The phasor sum of I3 and minus of I2 is IB. This angle is clearly 90 degree, and this is what we have written as per the mathematical formulation. And again you can verify it from the phasor diagram as well. We know that this total angle is, this one is 120 from I1 to I3, between I3 and minus of I2 60. So this one is 30. So when this is 30, So obviously the angle left between I1 and IB is 90 degree. Now here the line currents IR, IV and IY. They are lagging behind the respective phase currents by 30 degree. IR is lagging behind I1 by 30 degree. IY is lagging behind I2 by 30 degree. And IB is lagging behind I3 by 30 degree. So what we conclude that line currents lags behind phase currents by 30 degree. We can write IL is equals to root 3 times IP and angle minus 30 degree. So the magnitude is root 3 times and angle is minus 30 as compared to star connection where the line voltage and phase voltage have same relationship for the magnitude but their angle was plus 30. So this is what we need to keep in mind. So this is how we find out the relationship between line voltage and phase voltage in case of star connection and line current and phase current in case of delta connection. I hope with this video you are able to understand the phasor diagrams of both the star and delta connection supply systems. In the next video, I will drive the expression for power in three phase system. We will drive the relationship between the power of star and delta, impedance of star and delta, and then in the coming videos I will be solving the numerical problems of three phase system. Thank you for watching this video.